Hi, everyone. Let's get started on the final lesson of the workshop. My name is Alex. I'm a PhD student here at Berkeley, and I'm really excited to be here as part of the MP workshop. Today, we're going to be going over machine learning with Matminer, which is the code for data mining materials, as well as machine learning with scikit-learn and visualization with Plotly. So let's go ahead and find the Matminer directory in the workshop repo, and we will get started. So we're going to go into the lessons folder and then into 08 ml_Matminer. Here you'll find the notes for this lesson in this notebook, Matminer notes. And everyone should check and make sure that the exercises notebooks are there as well. If they're not, please ping somebody on Slack and they will help troubleshoot and we will get it figured out. But please make sure that those are there. So let's go ahead and create a new notebook in this folder. I want to introduce really quickly kind of what Matminer is. And I'm going to talk for a minute or two about this little graphic here to kind of describe what we're going to be doing today. So you can think of Matminer as a glue that connects important parts of doing machine learning for material science. It lets you easily retrieve data from repositories like the Materials Project, Citronation, Aflow, and more. It has feature extraction routines to convert materials primitives or materials objects in PyMatGen, like let's say a chemical composition or a crystal structure, into numerical vectors or matrices, which then you can use as input to a machine learning model. It connects to machine learning packages like scikit-learn and Keras. And although we don't develop these packages ourselves, it does have some easy interfaces to make building models a little bit easier. And it also connects to visualization packages like Plotly, which allow you to analyze your data visually, assess outliers, and do things of that sort. So the central object, what I want to highlight here is right here in the center is a data frame, which I believe most of you have already had some exposure to. This data frame is going to be the central object for all of these, and that's what we're going to be working on a lot this lesson. You can think of the data frame, if you weren't present for the previous lessons, kind of as like a big spreadsheet. So you might have a column for your materials, you have columns for your features, and you have a property, say you want to map it onto. And you'll note that if you're familiar with Excel, a lot of the things that we're going to do with a pandas data frame are pretty similar to what you can do in Excel, just programmatically. So in today's lesson, we're going to be going over 3 parts. In the first part, we're going to handle some Matminer data sets, which are ready to use and explore their data. We're going to get comfortable using data frames, and we're going to explore that a little bit. In the second part, we're going to convert materials data sets into features that we can use for our own models. And in the third lesson, we'll be creating our own model in the notebook and assessing its performance with scikit-learn and Plotly. Okay, so if everyone's ready, we will go ahead and make a new cell here. And let me just make some more room on this. And we'll get going. So in Matminer, I want to first talk about retrieving data sets. So in addition to pulling data from these online repositories, Matminer holds ready-made and pre-formatted cleaned data sets that you can download and use for your models. Matminer currently hosts over 40 data sets, with more being added consistently. And you can download and access them all in the same way. The object you'll be getting back is a data frame. So what we'll do to get a data frame back, well, actually, first, let's examine what kind of data sets Matminer has. So the way to programmatically do this is to import a get available datasets function from Matminer. So we'll type that out from Matminer.datasets, import get available datasets. And then we'll type get available datasets using tab complete. And then right and left parenthesis, and we'll shift enter that cell. And what we get returned is a list of strings of the dataset names. So you can see we have quite a few here. And if you scroll up, you'll see a lot more text output, which in addition to the dataset names, gives you a description of what is in that dataset, kind of a short summary. So you can see here for the steel strength dataset, there is the name of the dataset is steel_strength, which is just a string, which we'll be using these dataset names in a little bit. And its description is right here. And this is present for all of the datasets. If you're more of a visual person, you can also see them on the Matminer docs, which you can get to just by Googling Matminer datasets and going to the first link if you want a little more tabular view of the datasets that Matminer has. So let's actually get this dataset. If you're working on CoCalc, you'll need to do a little bit of IPython magic in the beginning. So we're going to type in env Matminer, Matminer data and data. So all this is doing is setting the environment variable for Matminer data to the data folder in our current directory. And that is where all of our dataset files will go. Next, we'll import from Matminer a pretty common function called load dataset, which is going to allow us to load any of the datasets in Matminer as a data frame. So we'll type from Matminer.datasets import load dataset. And then let's call that function to actually get a data frame. We'll make a new variable, df equals load dataset. And we're going to input the name of the dataset we want as the argument. So let's say we're interested in the dielectric constant dataset. We'll type that in, dielectric_constant. And let's shift enter to run this cell. And our dataset is ready to go as our data frame. If we want some more detailed information about this dataset, we can use Matminer's function getAllDatasetInfo, which is going to tell us a little bit more. So we can do from Matminer.datasets import getAllDataset_info. And then we'll print the output of this. So print getAllDatasetInfo, where the argument of this function is the name of the data set. So we'll do it for dielectric constant. And we'll shift enter to run that cell. And what we get out is a little bit more info than we had in the summary. So we can see the data set name, dielectric constant, and a short description. But we also get a list of the columns and what they mean, as well as some more info here about the number of entries and a reference. If you wind up using this data in a publication and you want to cite it, you can use the references given here. So now that we have our data frame, let's see what we can do with it. Let's use the head function, which is a method of a pandas data frame, to just examine the first few rows of our data. So we'll do df.head and shift enter. And here we see the first few rows of the data set that we downloaded. So we have some columns here for the material ID, its formula, just as a string, the number of sites, the space group, and so on. We also have the structure objects, which I imagine most of you are familiar with, now working with PyMatGen for a bit. And we have some potential target properties, like the band gap, the dielectric constant, and more. If we want a more programmatic view of the data that we get back, let's say the columns, we can just use the columns attribute of a data frame. So we'll do df.columns, and when we shift enter that, our output is the columns of this data frame as a pandas series. So just a vector of strings here. Another useful way to examine data in pandas, and what we'll do for our data frame, is the describe method. So we'll do df.describe. Running that cell, we get these aggregate statistics over all of our numerical columns. So our numerical columns being things like the number of sites, the dielectric constant, the band gap, cell volume. And we could see some various statistics here. The count, the number of entries here, the mean, standard deviation, as well as some percentiles and the maximum. So that can be an easy way to kind of get an overview of your data before you're using it. If you want to access specific columns of the data set, we can index it according to a regular Python, like you're indexing a list, basically. So if we wanted to index only the band gap column, let's say, of the data frame, we just type in df, and then with square brackets, the name of the column, band underscore gap, for example. And we shift enter this, we can see what we get out is 1,056 length vector of all of our band gaps with none of that extra data. So here we selected one column by indexing according to the column name. Alternatively, if you're interested in a row rather than a column, you can use the iloc method, ILOC. So let's say we're interested in the 101st row of our data frame. We can do df.iloc, and then the same indexing, but this time with an integer. So let's do the 101st. And since it's 0 indexed, that'll be index 100. And when we shift enter that, we can see we get that row for all the column names. So we've selected that row from our table, from our data frame. These ways of indexing data frames are useful for filtering the data set. So something you might want to do is remove columns that you're not going to use for machine learning, or remove particular rows that may be outliers or artifacts of calculations or what have you. So the way we can do that is, well, pandas makes it very easy. You can use the typical comparison operators like equals equals or greater than or less than equal to make the same sort of comparisons you would do for normal Python primitives like integers. So the way we'll do this is with a Boolean mask, which is just a series of true and false that we'll create using one of the columns in our data frame. And with that mask, it will select which rows to take. So let's make a new variable called mask, and we'll set that equal to, let's say we want to filter our data frame based on the cell volume. Well, we have a column called volume. Let's say we want to filter it to only those with volume more than 580. We can do mask equals data frame. We're going to select the volume column, and then we'll say more or equal to 580. But then we also need to index our data frame with this mask to select the correct rows. So we'll do df, and then we'll use mask as our index. And what we get out when you shift enter that cell, all of our entries match this criteria for volume. So we filtered our data set according to this pretty simple criteria. We can also do the same thing for columns. So let's say we want to remove certain columns. Like if we're going to create a matrix for machine learning, we might not want some of the columns. Like let's say we're going to remove the space group and number of sites. We can do that with the pandas drop function. So let's make a new variable called cleaned df, and we'll set that equal to our main data frame df dot drop, and then we'll input a list of the columns that we're looking to drop. So let's say we want to drop the columns nsites, space group, so space underscore group, e underscore electronic, and e total. And then we'll need to add in one more argument here, which is the axis we want to drop these over, because you can use drop on rows also, but here we're looking to drop columns. So we'll do axis equals 1 for columns If you wanted to do rows, you would do axis equals 0. So let's run that cell and then check our output using head. So do cleaned df.head. And we can see those columns that we dropped are no longer in our data frame. So our data frame has been cleaned by dropping those columns. More common, an alternative way to do this is just by indexing according to multiple columns. So whereas before we could type in something like df bandgap and get out the bandgap column, we can do a similar thing, but instead of this string, we can make it a list of strings. So a list of columns that we want to drop. So in this, let's do df, and then we'll make a list in here. And let's say we only want to keep the bandgap and structure columns. We'll do band_gap and structure. And when we run this cell, you can see the only columns that we're getting out are the ones that we selected, bandgap and structure. You can also create new columns with pandas using the same sort of indexing. Let's say we wanted to create a new column for the polycrystalline ionic contribution to the dielectric tensor. You can do this in the same way that we did comparison operators, by adding and subtracting, or by making comparisons, adding and subtracting. So you can use the same operators like plus and minus and divide and multiply that you do with normal Python objects, except with data frame columns. So if we want to apply a formula and make a new column, like let's say this formula, we have E total and E electronic already in our data frame, and we're looking to make this new column E ionic. So we can do that by typing in df, and let's call this new column poly ionic, and we'll set that equal to df poly total minus df poly electronic, and run that cell. And when we check the output, we'll see that our new column, you may need to scroll way to the right here, our new column is now in our data frame. So this is an easy way to apply simple math formulas to columns in our data frame for every entry. Okay, so that concludes the first part of this lesson. Now you should go to the exercises. So we'll go into files here in the 08 ML Matminer directory. We'll go to Unit 1 exercises. And we will start with this notebook. So in this first exercise, we're just going to load and examine a data set, and then we'll examine it some more later on. So with that, I'll give everybody 5 minutes or so, 5 to 7 minutes to look it over. Most of them should be fill in the blanks if you're looking in the notebook, and then we'll go over the answers together. So we'll come back here at 2:41 or so. Okay, hopefully that gave everybody enough time to do the exercises. We'll just quickly go over them. So in this first cell, all we're going to do is load a different data set, and then we're going to look at it a bit. So this only requires 2 commands, excluding an import. So first we'll type in from Matminer datasets import load dataset. If you're running in CoCalc, you may need to do the IPython magic command again, env matminer data, just to make sure that your data sets are in the right place. And then we'll set a new variable df equals load dataset, elastic tensor 2015. That is the data set that we're interested in. So that'll load it. But then to figure out the number of entries it contains and the largest value of the bulk modulus in the data set, which is in the k_vrh column, we can just use the describe function, which we used in the lesson a bit. So we'll do df.describe and run this cell. And we can see this is the described view. We have 1,181 samples. And if we're interested in the KVRH, the maximum KVRH is 435. So that's pretty easy. We'll go on to the next one, which is maybe a little more complicated. So we already have our data set loaded. If you didn't do the first exercise, you can just copy and paste that code into the cell. What we're going to be doing here is finding the number of entries in a data set where we're filtering based on the number of sites. And then we'll find the average number of sites across all the entries in that data set. So we can do the filtering using the Boolean mask that we showed in the lesson. So let's make a new variable mask equals df, and we're going to be filtering on the n sites column. So we're going to index n sites. And we're interested in entries where the number of sites is less than 20. So we'll do less than 20. Make a new variable called filtered df equals df mask. The number of entries in our data set, you can get a few different ways. One of the easiest ways is just by calling the len built-in function on it. So you can do a new variable n filtered equals len filtered data frame. And then the mean number of sites, you can use the .mean method, which I believe should be in the CoCalc notebooks as a hint. So you'll do mean n sites as a new variable equals filtered df. So we're going to select the column that we're interested in, n sites, and then .mean. And now let's just print that out in an easy way. So we'll do print number of entries in filtered data set, and then left and right bracket to format the string dot format n underscore filtered. And we'll also print out the mean. So print mean number of sites in filtered data set. Add some colons here just to make it look a little prettier. And do the same thing, format the string. So dot format mean n sites. And we run this code. See that we have 975 entries with the mean number of sites being equal to 8.5. Okay, now in the last exercise, you can actually do this 2 different ways. There is an easier way and a harder way. We're just going to be selecting the columns that we need to do machine learning on. So using our data set that we already have, all we need to do is a single line command to select the formula, structure, and KVRH columns. So we can do that by indexing according to a list. So So we can do df bracket, and then we'll make a list inside that bracket, formula, comma, structure, comma, k vrh. And we run that cell, we see that our columns are only the ones we wanted. Alternatively, you can use the data frame drop method, which you can see in the Unit 1 exercises answers, which is in the same directory as this notebook. But you have to enter in a lot more columns to drop. And in the interest of time, I'm going to skip the advanced exercise, but feel free to review that on your own and ask questions on the Slack if you have questions about it. Okay, so with the first exercise done, let's go back to the lesson and start part 2. So in this section, we're going to show how to generate machine learning descriptors or features from PyMatGen's materials objects, compositions, and structures. Matminer contains objects called featurizers, which convert from PyMatGen objects into vectors or matrices that you can easily use in data frames. So you can convert things like compositions based on the chemistry. You can convert crystal structures based on geometry or combinations of chemistry and geometry. And you can convert density of states and band structures. All of these will go into numerical vectors or into matrices that you can then use in your model. So the simple thing about this is that basically all of the featurizers work the same. They transform materials primitives into machine learnable features. So let's do a quick example. There will be 2 parts to this really. First, we'll go over how to do one sample. So for example, one composition, and then we'll go over how to do a bunch of compositions or a bunch of samples. So let's take an example here to kind of show what we're going to be doing. So in this example, we're going to convert iron oxide into a vector. These numbers in particular don't mean anything, but we'll do something that does. So first, we're going to import composition from PyMatGen. So we'll do from pymatgen.core import composition. And we'll make a new variable, fe203, which is composition. And then the string fe203. So let's run that. And as a trivial example, we'll just get the element fractions using the Matminer element fraction featurizer. So the way we can do that is by importing from Matminer. We'll do from Matminer dot featurizers dot composition import element fraction. And then we'll make a new object to instantiate element fraction. We'll do ef equals element fraction. We don't need any arguments there. Great, so now we have our featurizer as this object ef. And what this is going to do is it's simply going to tell us the fractions of elements in a composition. Now using the featurize method, which is present in all of Matminer's featurizers, you can get a vector back for this composition. So we'll do element fractions, a new variable, equals ef dot featurize fe203. And if you shift tab, you can see some of the arguments that this particular featurizer takes. So in this case, it's just a composition. That's all we need. So now let's execute this cell and print out the vector that we get. So we'll do print element fractions and run that cell. And we can see we get a vector that's pretty long, mostly zeros, except for 0.06 and 0.04. So if you're on the ball, you could probably recognize what these represent right away, but let's go into it real quick about how to get the labels for what each one of these features means. So for every featurizer, in addition to the featurize method, there is a feature labels method, which you can call to get the label for each feature that it outputs. So let's go ahead and do that and make a new variable called element fraction labels and set that equal to our featurizer ef dot feature labels. Don't need any arguments for that. And then we'll just print element fraction labels. Shift entering that cell. We see that we have the corresponding feature labels for each of the features here. We can get some more intelligible output by selecting the correct index for our non-zero features. So to prove iron oxide, we get the right numbers for it. Let's do print element fraction labels, and we'll select the 7th element, element fractions, also the 7th element. And we'll also do print element fraction underscore labels, the 25th element, and element fractions indexed also on the 25th element. So we shift enter this cell. We can see that our features make sense for the composition we were putting in. So that was kind of a trivial example, but you can also do these operations on entire data frames with one line of code. So let's featurize a data frame. Let's first get a new data set. Let's say the Berkeley super hard training data set. So we'll do from Matminer dot datasets import load dataset, and then df equals load dataset Berkeley underscore super hard training, which was adapted from the publication. And then we'll get a little summary by doing df.head. So running that cell, we can see the first few rows of our data frame here, kind of what we're working with. And let's say we want to featurize this according to the composition column. So in this composition column, each of these entries is a pi matching composition. And we're going to be applying the featurizer we just used to each of these compositions and getting out features in our data frame. So we can do this with Matminer. Each one of the Matminer featurizers has a featurized data frame method similar to the featurize method. And we need to call it with 2 arguments. The first one being the data frame itself, and the second one being the column we want to use as input. So let's first set our data frame as the output variable because we want to keep our features in the same data frame. And we'll do equals EF, our element fractions featurizer, featurize underscore data frame. And if you're interested, you can shift tab in these parentheses to see some more of the arguments. But the only ones we need are the first, which is our data frame as input, and then the column that we want to use to select to use as input. In this case, it's composition, because we're going to generate composition features for every one of these samples. So let's go ahead and type in composition. And then after that, let's do df.head to examine our data frame. So shift tab and running that, we get a little progress bar. We get the first 5 rows. And at first it doesn't look like it's done anything, but if you scroll over, you can see the element fractions are printed here. Inconveniently, none of these are non-zero in this view, but you can select, using the skills you learned earlier, you can select certain columns or certain rows and see that the features were generated correctly. We can do the same thing for structure featurizers. So applying an algorithm to generate numerical features from a crystal structure based on its geometry or many other features. So let's go ahead and load another data set. We'll do df equals load dataset. And this time we're going to use the phonon underscore dielectric MP dataset, originally from the materials project. And we'll do df.head to get an idea of the data we're working with. So when we shift enter that cell, we see we have some inputs and some possible outputs to say fit a model onto. And we're interested in applying a featurizer to the structure. These are actually not strings in here. These are PyMatchN structure objects contained in this data frame. So let's apply a featurizer called density features to this data frame. What we'll do is we'll do from matminer.featurizers.structure import density, capital D, features, capital F. And we'll make an object for that. Let's call it density F equals density features, tab complete. Don't need any arguments there. And then we'll see what this featurizer can do. So we already know how to do that using feature labels. So we'll do density F dot feature labels. So before we apply the featurizer, we can see what we're going to be getting. So we can see we're going to be getting 3 features: density, VPA, or volume per atom, and the packing fraction. So for each structure here, we'll be getting 3 numerical features back. So let's go ahead and apply this to the entire data frame, just like we did for element fraction in the other data set. We'll do df as our output, because that's where we want to store our generated features. Density f dot featurize data frame. And then the first argument being our data frame. And this time, for the second argument, the column that we want to use as input, instead of composition, we want to use the structure column as input. So let's go ahead and type that in, the column name, structure. And then after that's done featurizing, we'll examine our features with df.head. So let's shift run that cell, get a little progress bar. And in our data frame, our features are there for every sample. Okay, now we'll go on to another kind of featurizer, which are mostly used for data munging or conversion or pre-processing, called conversion featurizers. So to use conversion featurizers, they work more or less the same as the rest of Matminer's featurizers. And what you'll see in this tutorial will basically apply to all of the conversion featurizers. So things you can do with conversion featurizers is, say, convert from a string composition or a formula column to a PyMatchN composition. And you can do it in an error-tolerant fashion. So let's go ahead and do an example. We'll do from matminer.featurizers.conversions import. Let's do that example, string to conversion. So we'll do str, capital T, capital C. Oh, sorry, this should be composition. String to composition. And we'll make a new object, stc, string to composition. And now let's actually run that on our data frame. So we can see here in our data frame, we have this formula column. These are not PyMatchN compositions. These are simple strings. So what we're going to be doing here is converting them into compositions, which then we can use with any of the other featurizers. So we'll do df equals stc dot featurize data frame, because we're applying it to a data frame. First argument is the data frame, and the second is the column we want to use as input. So in the previous example, it was structure. In the example before that was composition. Now we want to apply this featurizer to convert strings in the formula column to compositions. So we'll do formula. And then we'll look at the output with df.head. Okay, so now previously, where there was no composition column, if you scroll over, now in our data frame, we have this composition column with all of our PyMatchN compositions right here for us to use. And these can be used downstream for more featurization tasks or other conversions, things like adding oxidation states in a fault-tolerant manner. I'm running a little bit short on time here, so I won't go too much into the advanced capabilities. If you look in the notes, you'll notice that there are two other main arguments you can use with featurized data frame, which are ignore errors and return errors. So if you have messy data, you can use those to kind of filter them out. And when they do fail, you can examine the errors. Another useful method in Matminer, which all featurizers have, is the citations method, which is important if you want to use Matminer in a published work and you want to use some of the methods that we're taking from other published papers and want to get the correct citations without having to comb through tons of code. You can just use citations. So let's get a brand new featurizer. Let's say the global instability index featurizer. We'll do from Matminer.featurizers.structure.bonding import global instability index with capital G and capital I and capital I. And then all we need to do is make an instance of that object. So global instability index with a constructor there, and then dot citations, calling the citations method. So when we shift enter that cell, don't worry about this warning here, we'll see that we get a bib text formatted list of references. And these are available for every featurizer. Okay, so that concludes the second lesson. So let's move on to the exercises for this lesson. We'll go to Files and Unit 2 Exercises, which I forgot to clear the output from. And let's give it till, let's say 7 minutes from now, so 3:10, for you guys to look over the exercises. And then we'll go over the answers at 3:10. Okay. Okay, so hopefully everybody has finished the exercises, or at least given a good attempt at it. We'll go over the answers now. So first, you should just run this cell to kind of get a starting point for these exercises. That's just going to load a pre-cleaned data frame so we can kind of start fresh here for these exercises. In the rest of the exercises, I believe there should be some blanks for you to fill in, but I'll type everything out just in case. So in this first exercise, we're going to use a conversion featurizer, like the last one we used in the lesson, to convert the formula column into compositions. So just like we did before. So let's import from Matminer featurizers structure, or sorry, conversions. Import str to composition. Let's then make an instance of that class with stc equals str to composition, and we'll just tab complete that. And from our data frame, we'll set that as the output. So we're putting all of our features into our original data frame equals stc dot featurize data frame. The data frame is the first argument, and our input column, which in this case is the formula, as our second. And then we'll just check it out to make sure that our features were added correctly, which in this case is just the composition objects. And we can say they are. In the second exercise, we're going to add some composition features using this composition column. And we're just going to use the exact same featurizer we did before, element fraction. So kind of just repeating the steps here. We'll do from Matminer featurizers composition, import element fraction. And we'll make an instance of that class, EP equals element fraction. Let's do EF. That makes more sense. And we'll do the same thing we did above, except with this new featurizer. So df equals ef dot featurize data frame. Still using our data frame as input, so df as the first argument. And the second argument, the input column, is just going to be composition, which is the column we just made from the conversion featurizer. And then we'll print that out with df head. And we have all of our element fraction columns. And then finally, we'll do the same thing, just repeating what we did in the lesson with density features. So from Matminer featurizers structure, import density features. And we'll make an instance of that. So we'll just do DE equals density features. Then we'll apply it in the exact same way. df equals DE dot featurize data frame. First argument being the data frame. The second one being, you guessed it, structure. And then we'll do df dot head to make sure that our three features are generated correctly. So we ran it. Now we have at the end here, the density, the VPA, and the packing fraction structural features for all of our samples, all 1100. Okay, so we've generated our features. Let's go on to the next section. If we go back to our notebook here, we can start the final section, which is a bit long. So we're going to move a little bit fast. If you get lost or fall behind, just send a message in Slack and I'll slow down and try to adjust. In this section, we're going to be creating, training, evaluating, and visualizing a machine learning model using some of the tools in scikit-learn and Plotly and how they interface with Matminer. So let's first load and prepare a pre-featurized model. So as if we had gone through the previous steps of this in an ML pipeline. We can do that by typing in import OS, So we're going to find the file in our resources directory in this folder. And then from matminer.utils.io, import load data frame from JSON. And we'll do df equals load underscore data frame underscore, oops, load data frame from JSON. And we'll do os.path.join our resources directory. If you're using this on your local machine and you have the file somewhere else, you can just type in the path. We'll join that to the name of the file, elastic tensor 2015 featurized.json. So all of these Matminer featurizers, when you put it in a data frame, can be serialized to a JSON format, which you can transfer between machines, upload online, and basically do whatever you want with. You can persist. And then let's just check that our features were loaded okay. So we'll do df head. So let's go ahead and run that. See, it's loading. If we scroll up, we have our data frame, which contains some formulas, structures, and KVRH, which we're going to use in this example, this bulk modulus, as a target property, so something we're trying to predict. And we have all of our features along here, which we can only see a few of because there's so many. So the first thing we need to do if we're going to make a model for predicting bulk modulus is we need to have our target values in a format that scikit-learn can understand. So you can pass in pandas series, in other words, just the columns if you want. But in this case, we're going to get the NumPy array out of it just to demonstrate how you would do that. So we'll make a variable called y, and we'll set that equal to our data frame and our index it according to our target value, which is bulk modulus, so KVRH. And then we're going to use the dot values attribute to get out a NumPy array. And then we'll just print it. So print y. Great, and there are our target values. So that's pretty easy. Now we also need to get our features for training, which might be a little bit more involved because we're going to be selecting a matrix rather than a single vector. So let's make a new variable called x, which is going to be our training features. And we're going to set that equal to everything in this data frame besides the stuff we don't need. So we'll do x equals df.drop. And the columns we're going to drop, the things we don't want showing up in our matrix is if you scroll up here. We don't want the structure, the formula, and especially the target value. And we don't want the composition in our training features. We're trying to map these learning features that we generated onto our target value. So let's drop these 4 columns. So in drop, we'll type in the names of the columns we want to drop, which is structure, comma, formula, comma, composition, and our target value, KVRH. And we also want to specify axis equals 1 to make sure we're dropping the columns. So let's run that. Now we have our feature matrix. Let's print out some info about it. So we can do print, and let's type in there are brackets to format possible descriptors, and then dot format. We're going to do the length of the columns of x, so the number of columns that are left in our feature matrix. And we'll also just print them out. So we'll do print x.columns. So we have 135 possible descriptors. We have 135 features. And these are a few of them that we can see in this vector here. So now we're going to train our own model using scikit-learn and these features that we have ready. So the model we're going to train is a random forest regressor, and we're just going to go through the very basics here. But what we're going to do is first we're going to train on the data to evaluate the training error. And then we're going to run a cross-validation where we estimate the error more accurately. So let's first import our model. We'll do from sklearn.ensemble import, and we're going to use a model called a random forest. So we'll do import random forest regressor. And we'll make a new instance of that called RF equals random forest regressor with 2 arguments. The first one being n underscore estimators, and we'll set that equal to 100. And the next one being random underscore state equals 1. So this n estimators parameter is an example of a hyperparameter in a machine learning model. So this is something that you set before fitting your model. This is not something that you can determine 100% what is going to be the best one beforehand. You might have to try a bunch of them or have some strategy for trying out different hyperparameters. But for the purpose of this lesson and to keep it short, we're just going to use this one where n estimators here is the number of trees which are in our random forest. So the number of independent estimators. And this random state argument is just to make sure that we all get the same answer. So now let's actually fit our model. All of scikit-learn's models have a .fit method, which is pretty convenient. So for this one, if you guess we were going to be calling fit on it, you're right. We'll do rf.fit, and the arguments are our feature matrix, which the model will be mapping onto y, our target values. So let's run it. Oh, I forgot to run this cell. Okay, now we can run it. Might take a second or two, especially if we're all running it at the same time on CodeCalc. And that's it. We've actually fitted our first machine learning model just like that. Now let's see what our predictions look like. So let's make a new variable called ypred and set that equal to rf. And similar to fit, all of scikit-learn's models have a predict method. So we can do rf.predict. And what we're going to use to predict is our training matrix. So we'll run that. And now we have a vector of our predicted values. So let's examine our training error. And we'll do that with a few nice things from scikit-learn and NumPy. We'll calculate the root mean squared error. So let's first import NumPy as NP. And then from sklearn.metrics, import mean squared error. Make a new variable called MSE for mean squared error equals mean. Oh, it doesn't want autocomplete for me. Mean squared error. And the 2 arguments we're going to use, if we shift tab. Oh, I haven't imported it yet. Sorry, excuse the scrolling. The 2 arguments, which if you import this and then check it, are the true and the predicted values. So you can see y true here and y predicted. So what we will do is input y and ypred in here to get the mean squared error. And then we'll print out what the root mean squared error is that we can get with NumPy. So we'll do print training RMSE equals, and then some formatting syntax for the decimal. So we'll do :3 gigapascals. And then dot format np dot square root our mean squared error. So let's run this cell. We can see our training root mean squared error is 7 gigapascals, which if you think about it is pretty good. But this is not what the actual error is going to be, because our goal with this model is to eventually apply it to some new samples which are not in the training set. All we've done here is trained a model and then predicted on those exact samples what it's going to be. So this training error is way underestimating what our real error is going to be. So a way we can more accurately evaluate the error is using cross-validation. If you're familiar with cross-validation, I'm sure you don't have to listen to this part, but if you aren't, cross-validation is a better way to evaluate error. So we run a number of independent experiments, which we'll call folds. And in each experiment, we separate our training and testing data for assessing error. So something we might do in one fold is take 90% of the data for training and keep 10% for testing or for validation. And then we repeat this a certain number of times, let's say k times or 10 times. And then we get 10 scores showing how each of our little experiments did. So scikit-learn has some convenient methods for doing this. So we'll import them now. We'll do from sklearn.model selection import kfold, and we'll make a new kfold object. We'll call it kfold equals kfold, and we'll define the number of splits here. So the number of experiments we're going to do. We'll say n splits, n underscore splits is equal to 10. It's a pretty standard number for cross-validation. We'll also specify random state equals 1, so we all get the same answer. And then finally, we'll add shuffle equals true, which in combination with random state will randomly shuffle the data, but then also make sure we get the same answer here. So let's go ahead and run that cell. And now we can get our scores on each experiment now that we've defined our cross-validation scheme. So let's do from sklearn.model selection import cross-val underscore score. And what this is going to do is it's going to give us back, in our case, 10 scores for each of our experiments. So 1 score for each of our folds. So I'll make a new variable, scores equals cross-val score. And the inputs for this are going to be our model, which in this case is going to be refit by this function. So internally, it will be fit on the splits that it's defined by the cross-validation scheme. Then we'll add in our feature matrix X and our vector of target values Y. The scores we want to return are, let's say, the root mean squared error. So let's calculate with the scoring parameter set to neg underscore mean underscore squared error. And then we also need to pass in our cross-validation scheme. So we'll pass in CV as another parameter is our kfold. Now we can actually get the scores out. So we'll do, actually, let's run this because this takes a little bit to run. So let's go ahead and run that. And while that's running, hopefully we don't crash CodeCalc here. We'll make a new variable called RMSE scores. And we'll do a little list comprehension. So RMSE scores equal to list np dot square root absolute value of score for S in scores. So we're just going to iterate through these 10 scores. Oh, and it just finished running. We're going to iterate through these 10 scores, take the absolute value of each one, and then square root them. And then we'll get out for each of our experiments what the scores are. But probably what we're most interested in is the mean RMSE among all these folds. And although you might be interested in the particular performance of a fold, which you can examine from this array, let's just print out the mean RMSE. So we'll do print mean RMSE, and then some Python formatting for the string, which we'll just have as 3 decimal places. And then dot format np.mean of our score array, RMSE underscore scores. So when we run that, we'll see our mean RMSE now is 18, which is almost 3 times as much as our training error. So here we see a more realistic estimate of how our model's doing. Now, overall, this mean RMSE, it still isn't too bad for this model. But this is an example of the kind of scheme you should use to try to evaluate errors rather than just using the training error. Now, another way we can evaluate our error is by looking at some graphs. So in this next section, we're going to make some graphs with Plotly that we can examine our error a little bit more visually. So first, let's put some predictions in our data frame for every fold. So this cross-val score function got us the score for every fold, but really what we want is a prediction for every sample. So what we'll do is from sklearn.model_selection, we'll import another function called cross_val_predict. And then we'll use that for a new array called y_pred, which is going to be our predicted samples in our cross-validation scheme. And we'll set that equal to cross_val_predict with the same arguments that we had above for cross-val score. So we'll do our model, which it'll refit internally, x, comma y, and then our CV. Note, we don't actually need the scoring parameter here because while this cross-val score is returning scores, this is only returning the raw predictions. So we'll do CV is our same k-fold. And let's go ahead and run that because that might take a little bit to run. Now, while that's running, let's start typing out some code for putting this into our data frame. So let's use our df and we'll make a new column. Let's call it kvrh predicted. And we'll set that equal to what y predicted is going to be. Then we'll make another column for some further analysis for the percentage error. So let's call this column %_error. And using the skills we learned in part 1 of this workshop, or part 1 of this lesson, we're going to write our own formula for the percentage error. So we'll do data frame, the true KVRH column, minus df KVRH predicted. So our predicted column. And we'll use the convenient pandas method .abs to take the absolute value of that resulting series. And we can continue this by dividing by the true value, k_vrh. And then finally, we'll type *100 to multiply by 100 and get the percentage. And our previous cell is done executing. So let's print out what we get. So if you scroll to the top here and then go to the end, you'll see now we have for every sample our cross-validation predicted KVRH. And we have the percentage error for every sample. So some samples we're doing pretty good when we have a percentage error of say 3%. Other ones, not so good. We have 13%, and I'm sure a lot higher. So we're running a little bit short on time, and this lesson is long, so I'm going to kind of speed through this part. But now we're going to examine it visually. And I would recommend looking at the Plotly documentation for a lot more info on how to use Plotly. But for those of you familiar with Plotly, I'm just going to type out the expressions here. So first we'll import plotly.express as px. And what Plotly expresses is just an easy way to graph data frames with Plotly. And then we'll import plotly.graph objects as geo. What we're going to do here is we're going to plot on the x-axis the true KVRH and on the y-axis the predicted KVRH, so we can see where our model is failing and how it's failing. So first, let's make a reference line, which is just 1-to-1. And if our predictions are exactly on this line, that means we did very well. So let's make a new variable, reference line equals go.scatter. And we'll type in some arguments. We'll have our reference line go from 0 to 400 gigapascals. And our Y series go from 0 to 400 gigapascals. So it's just a 1-to-1 line. And we'll type in some arguments, which are not important for the purpose of this lesson, just for making it look nice. Make the line black, and we'll make the line dashed also. And we don't really want our reference line to show up on the legend, so we'll add this command show legend equals false. Okay, now we're going to make the main figure with Plotly Express, which is the easiest way to make interactive graphs from data frames, with Plotly at least. So we'll do fig, which is going to be our Plotly figure, equals px.scatter. We'll be making a scatter plot of our errors. We're just going to input the data frame, and then we're going to name for each of the things that we want to show just the column names. So on the x, we want to plot according to our true bulk modulus. So x equals k underscore VRH. In our y, we want to use the predicted one. So we'll use k VRH predicted. We also want to display some info on hovering over the samples. So we'll do hover name, and we'll set that equal to the formula column. Let's also color them according to the percentage error. So we'll type that in, color equals percentage underscore error. And then finally, we'll set a color bar, which you can find more out about on the Plotly documentation. So we'll do color continuous scale equals px.colors.sequential. And let's make it blue and red. Now we have our figure. Let's add our reference line to it. So we'll do fig.add trace, add our reference line. And then we'll do fig.show, show it in the notebook. So hopefully I typed in everything correctly here. It's a lot of typing. And we have our graph. So we can see right away that there are some outliers we want to be aware of, like this one, where the true KVRH is much higher than the predicted one. This is for carbon. I'm guessing for diamond. Interestingly, though, the percentage error, even for this very bad prediction, is not as bad as some others, like for this, for water, where the KVRH is off by an absolute value of less than carbon is, but the percentage error is much higher. So using Plotly, we kind of get an idea of what our data looks like. For the most part, it's pretty near to this line, which is our kind of perfect performance line. So our model's doing all right, but it has some problems with some of these outliers. So these are ones that on closer inspection, we might want to take some time to look at the features that we're using to predict on, look at the model hyperparameters, and then improve from there. You also want to interpret your model in any way you can. So if we were interested in, say, the most important features that we generated and how they influence the random forest model, we can do that with scikit-learn. So let's go back to our model, RF, and we're going to use this attribute called feature underscore importances underscore. So feature importances underscore. And what that's going to return is for every feature that we passed in, the relative importance of it in the model. So when we shift enter this cell, we can see we get back a NumPy array with all these numbers. Making sense of them like this is a bit hard. So let's use Plotly again and get an idea of our most important features. So in this, we're going to get our importances as a new variable. We'll set that equal to rf.feature importances underscore. And we want to have this other variable included, we'll call it, equal to the value of the columns. So x.columns.values for our feature matrix. And then we'll sort the indices of these features according to which ones are going to be the most important. So we'll do indices equals numpy.argsort importances. And then this bracket at the end is just going to reverse the list. So we'll do : -1. Now we'll make our figure. We'll do fig, let's call it fig bar, equals Plotly express px dot bar. We'll set our x-axis equal to included indices. Say the top 5 most features. So we'll do bracket 0 to 5. We'll set our y equal to the importances on the most important indices, 0 to 5. We'll make a nice title for it. We'll say title equals feature importances of random forest. And then we'll add some labels for the axes. So we'll do labels equals dictionary X feature, because that is where our features are going to be, and then Y importance. And then finally, let's do fig underscore bar dot show it in the notebook. And here we have a little graph outlining what the most important features according to our random forest model were. So we see that the most important feature by far is the mean melting temperature, according to the MAGPIE data featurizer, followed closely by the volume per atom, or maybe not so closely, but in second place is volume per atom. And below that is the minimum melting temperature and density. And so these features kind of intuitively make sense because we are predicting the bulk modulus. So this is just an example of how to get the feature importances and put them in a form that you can understand graphically. Okay, so I realize we're over time now, but I figured we will maybe just quickly go through the Unit 3 exercises and call it there. So let's go to the Unit 3 exercises. I'm thinking since we're a little short on time, we can just do them together. We'll go to our folder, Unit 3 exercises, and we'll just fill them out together. So in these exercises, we're going to use a pre-featurized data frame to kind of do the same thing we did in the lesson. So let's just load the exact same one. This is the same code that was in the lesson already. Got our data frame ready to go. Now let's split it into our target property and our features. The target property in this case is going to be in the total dielectric column. So let's pay attention to that. And then the features are all the other columns except for structure and composition. So if you can think fast, you've probably already filled this in. We'll do y equals total dielectric dot values. And our x, all we're going to do is drop structure and composition. And also our target value. We don't want our target value in our training features. Let's go ahead and run that. Great. For the second exercise, we are going to train a random forest model with slightly different hyperparameters. If you remember from the main lesson, we had 100. Now we're going to use 150. And then we're going to use the model to get predictions for all the samples and store them in a variable called ypred. So we will import random forest regressor, and then filling in the blanks, we need to specify our number of estimators for instantiating the class. So we'll type in estimators, n underscore estimators equals 150. And then using the fit method, we'll fill in these. Our target features are x, or sorry, our features are x and our target values are y. And then finally, we'll get our values in ypred. So we're going to predict on our target features and get them out in an array. Might take a second to run. And then if we run this, which should already be filled out in your notebook, see our training RMSE is 6.0. But as we discussed in the main lesson, this training RMSE is not super representative of how this is going to do it in the real world. So for the third exercise, we're going to do a k-fold cross-validation. So in this example, we're going to do it with 5 splits instead of 10, like we did in the lesson. So we're going to import the same k-fold class and the same cross-val score class. We're going to make a k-fold object by filling in the blank here with n underscore splits equals 5. And then we're going to fill in all the required arguments in scores. So we'll do scores equals cross-val score, the first argument being our model, which is going to be internally refit. And then our training features, x. And our target value is y. And then finally, we want to set our CV parameter equal to the k-fold we just created right here. So let's go ahead and run this. That might take a second. And then all we're doing in this next cell is the same thing that we did in the main lesson. We're just going to print out the mean RMSE among all of the 5 splits which we calculated. Okay, great. Just finished running. So then let's run this last cell. We see our mean RMSE is 20.5. Okay, so with that pretty much brings the end of the interactive part of this lesson. Just at the end here, I wanted to mention that in the notebook, there is a mention of MatBench, which is a set of benchmarking data sets that are accessible through Matminer, and which there is an online leaderboard for comparing machine learning models. So if you have your own ideas for machine learning models and want to compare them on some benchmarks, you can use those. If you're interested in trying out the MatBench datasets, I'll just run one last cell here. You can use the same load dataset function from Matminer. So we'll just do from matminer.datasets import load dataset. And all of the MatBench datasets begin with MatBench in the name. So you do df equals load dataset. And then let's do, for example, the MatBench steals dataset. And all of these are pre-cleaned and ready to use. So if you run that and then look at the data, you'll get out a pretty minimal data frame, which has already been pre-curated for benchmarking, for running your own models on. All of these datasets are also available on MP-Contribs, specifically the MP-Contribs ML deployment on Materials Project. So if you're interested in looking at them more, you can do it there, as well as downloading them through Matminer. You can also look at the website, which is going to be hosted at matbench.materialsproject.org. Currently, it's at this address, hackingmaterials.lbl.gov. And if you have an algorithm you would like to submit, please make a submission. There are instructions for it on the website. There's lots of, oops, I forgot the MatBench here, /MatBench. You can make a submission. The instructions are on this website. And with that, I will conclude this lesson. I want to thank everybody for their attention and their patience for allowing me to go over time a little bit. And thank you again.